5.2, binomial probability distributions. We've already done probability distributions. That was a table showing all of the probabilities. Binomial probability distribution is just a special kind, okay? Binomial. And you've seen the word binomial before. We know binomial kind of implies that there's two things. Keep that in mind. Binomial probability distribution results from a procedure that meets these four requirements. The procedure has a fixed number of trials. One trial is a single observation. The trials must be independent, meaning the outcome of any individual trial doesn't affect the probabilities in the other trials. Outcomes of each trial are classified into two categories, success or failure. Either I did or I didn't. The probability of a success remains the same in all trials. So we've got those four things in order to be a binomial probability distribution. Variables you'll see, N is the number of trials, X is the specific number we're looking for. So maybe 3 out of 5 or 7 out of 10 or whatever. 10 is how many total trials there are, X is our number that we want. P is the probability of success, Q is the probability that you don't succeed. So if the probability of doing something is 0.2, then the probability of not doing that thing is 0.8. And you've got a little formula for this. 0.8 is just 1 minus 0.2. That's what we're doing. And so that's pretty easy to think about. Those two numbers have to add up to 1 because either it does or it doesn't. 0.2 probability of doing it, 0.8 probability of not doing it. That's what we're talking about. There's your binomial. There's your two different things. Either you do or you don't. And then px is the probability of getting exactly x successes, x of whatever we're after. Number 1, Twitter. When an adult is randomly selected with replacement, there's a 0.85 probability that this person knows what Twitter is. Suppose that we want to find the probability that exactly 3 of 5 randomly selected adults know what Twitter is. Does this procedure result in a binomial distribution? Okay, so remember from above, a binomial distribution had 4 things to look for. A binomial probability has these 4 things. So that's kind of what this question is asking. Does this situation have those 4 things? So we've got 5 trials. We're selecting 5 adults. So that's fixed. So that's good. Number 2, results aren't affected by previous. Okay, each time we select an adult and ask them, it's not going to be affected by the one that we asked before. That is independent. So that one's good. 3, either they know or they don't know. That's your 2 things. That's your success or failure. And then 4, the probability is 0.85 every time. So it's the same every time. All 4 of those things are good. All 4 of those things are valid. So therefore, does this procedure result in a binomial distribution? Yes, because those 4 fit. So then part B says identify the values of N and X and P and Q. This is more like it. N is how many trials there are. That's 5. X is how many we're specifically looking for. We're specifically looking at 3 of them. So X is 3. N is 5. X is 3. P is the probability that we're after. Okay, and they came right out and told us the probability was 0.85. They're probably never going to tell you Q, but it's always easy to figure out because it's the number that's going to add up to 1, right? You got 85%. The other percentage must be what? 0.15, yeah, 0.15. 85% chance that it happens, 15% chance that it does not happen. There's your binomial. 5% guide for cumbersome calculations. We've already seen this. They keep kind of bringing stuff back from older lessons. When sampling without replacement and the sample size is no more than 5% of the size of the population, treat the selections as being independent, even though they are actually dependent. So remember how we needed this condition. We need them to be independent. So this is just like a guess. Every once in a while, this will come into play. We can just assume it's independent. Methods for finding binomial probabilities. Method 1 is a formula. And you're not going to like this formula, and honestly, I don't like it either. And then I'll show you an easier formula. So the probability that exactly X things happen is going to look something like this. N factorial over quantity N minus X factorial times X factorial times P to the X times Q to the N minus X. I think that formula looks really, really difficult, but let me clean it up for you. This is just a combination, okay? That's literally the formula for combinations. So I would much rather see the problem written like this, NCR. It's a combinations, it's a group from a group. We're selecting a group of items from a larger group of items, 3 out of 5 maybe. And then what you're gonna do is you're gonna take that number times the probability to the, wait, why did I put R? I shouldn't have put R, I should have put X. That's an X right there. NCX. And so times the probability to the X power times the non-probability to the N minus X power. And that formula still looks really complicated, but once you see an example, you're like, yeah, that makes sense. Okay. So we've got these variables. There's N, there's X, there's P, there's Q. We got to know those for each problem. Now, method 2 is technology. And those of you with TIs, you're gonna want to figure out how to use this. Okay. It's inside the distributions menu, and I believe that is on top of a button. So you'll have to hit the second button to get there, but check that out. Binom PDF is what you want to find the probability for one value of X, and then binom CDF. C stands for cumulative, and we know from our cumulative GPAs that adds up all the semesters, right? Okay, so cumulative probabilities, I guess I didn't have to write it because it was right there, but cumulative probabilities are going to add up all of the probabilities from 0 through whatever number you're looking at. Okay, so basically it's going to be probability of 0 plus probability of 1 plus probability of 2 plus up to whatever number we're looking at. Cumulative, add them all up. The other method, if you don't have a TI, go to your math sites on Goldadder and find the math site that's talking about binomial distribution. That's what we're looking at. Honestly, I kind of like the website better because it gives me more stuff. It gives me more options. With the TI is great. The TI will work, but you might have to put a little bit more thought into it. All right, both of them are good. Back in my day, we didn't have any of that. We had to use that formula. Okay, so you're lucky. Example 2. Here comes that Twitter question again. Given that there is a 0.85 probability a randomly selected adult knows what Twitter is, find the probability that when 5 adults are randomly selected, exactly 3 of them know what Twitter is. Okay, so we want to find probability of exactly 3. X equals 3. Sometimes we'll want like greater than or less than or something like that, but we want to find 3 out of 5. So if I'm using the formula, how the formula works is this. We've got 5, choose 3, times the probability is 0.85 of this happening, and I want 3 of them. 3 of those people are the 0.85s, and what's going to happen is that's going to leave 2 of them to be the 15s. It's got to add up to 5 because there's that many people in this survey. So 3 of them are successes, 2 of them are failures. That is the formula. So if you're typing this in according to the formula, you'd say 5, choose 3 times 0.85 to the third times 0.15 to the second power, and we get that. Okay, now I like I like 4 decimals, so 0.1382. Or so. We have like 1 minute left. All right, let's stop there for now, I guess. If we want to do this problem on a TI, here's what we'll do. We can go into the distribution menu and arrow down a bunch of times to Binomial PDF. Trials is 5, N is 5, and your p-value was 0.85, and your x value on this problem was 3, x equals 3. Paste it to your home screen, and there we go, same answer, 0.1382, right? If you want to do this, or if you don't have a TI, you can go into Goldadder's math sites and find the one that says binomial distribution. So when we get to this site, the probability of success was 0.85. There were 5 trials and 3 successes. Now this gives me more than what I need, but what we need to look at is this right here says x equals 3. X is less than 3, less than or equal 3, greater than 3, greater than or equal 3. We definitely want to look at just when x equals 3, so there's our number, 0.1382. Same thing. Between 1974 and 2011, there were 460 NFL football team or overtime games. 252 were won by the team that won the coin toss, and they want to know if this result is significantly high. Significantly high. So this is a concept we've seen before. We can test by looking at the probability of x or more, and we're concerned at if that is less than or equal to 0.05. So find the probability of x or more and see if that's less than or equal 0.05. All right, so let's look at this problem. 460 NFL overtime games, that's N. 252 is your X number. And we're talking about a coin toss here. So coin toss, that's 50-50, right? So the probability of winning would be 0.5 and the probability of not winning is also 0.5. Those are our numbers. So here's the tricky thing. When we want the probability of X or more, in this case, we want the probability of 252 or more. 252 or more. So what I'm going to say is I want to look at where X is greater than or equal to 52. Now that's very, very tedious to do by hand. So if we were going to calculate that with the formula or by hand, we'd have to find 252 and 253 and so on and so on and so on, all the way up to 460. That's a lot of formulas. Calculate, add them together. There's got to be an easier way, and there is with technology. So with the TI, it's a little bit confusing because when you look at this and we want greater than or equal to 252, that's not how binomial CDF works. Binomial CDF, C stands for cumulative, so it is going to add some stuff up, but it's not going to add up from 252 to 460. What CDF does is it adds up from 0 to your number. Okay? So in order to do what we need it to do, if you think about this problem, if we want 252, 253, and so on and so on and so on up to 460, think about what we don't want. We don't want from 0 to 251. And so what we can do with our TI is we can say 1 minus the binomial CDF from 0 to 251. Okay, and so let's just type that in. We'll go 1 minus. We've got to go to our distribution menu again, arrow down. This time we want cumulative. So binom CDF. Trials was 460. Probability was 0.5. X value is 251. This is tricky, okay? So what this is going to do is this is going to add up from 0 to 251. And we're going to subtract that from everything because these are the ones that we don't want. 0.02242. 0.02242. Okay, so that's 460, comma, 0.5, comma, 251. Kind of tricky, right? Probably the faster way to do it is to go to this site and just say, all right, probability of success is 0.5, number of trials 460, and number of successes 252. That's the number that I'm looking at. And so I calculate that and understand that we want greater than or equal to that number. So here's our number right here, 0.0224. There it is. I like this site a lot. I like the TI a lot too, but this is probably faster to use the website. So what have we found? The answer is not 0.0224, because remember the question was, are we significantly high? So notice your number 0.0224 is less than 0.05. So this means the results are significantly high. Okay, so what? So what this does is it rules out random chance. So what? Remember how we won 252 games? All right. We can conclude that the team that wins the toss has a greater chance of winning. Okay. These numbers are significantly high, implying that there is some sort of relationship. Okay. Winning the coin toss is advantageous. Number 4, devil of a problem. Based on a Harris poll, 60% of adults believe in the devil. Assuming we randomly select 5 adults, find the probability that exactly 3 of the 5 adults believe in the devil. So 60% is P, and 3 is our X, and 5 is our N. The only thing they don't give me is Q, but that's easy to figure out. Q must be 40%, or 0.4, right? 0.6 and 0.4, those are our numbers. So exactly 3. We want exactly 3. So according to the formula, we'd have 5 choose 3 times 0.6 to the third times 0.4 to the second. Remember, those two exponents have to add up to 5, and that's what we've got. So we can do that on most calculators. This is the formula, 5 choose 3 times 0.6 to the third times 0.4 squared, 0.3456. Part B, we want the probability that at least 2 believe in the devil. So at least 2 means greater than or equal to. In other words, 2 or 3 or 4 or 5. So if I was going to use the formula, I would have to say 5 choose 2 times 0.6 to the second, 0.4 to the third. Or means plus. 5 choose 3 times 0.6 to the third times 0.4 to the second. Or we've done 2, we've done 3, now we do 4. 5 choose 4 times 0.6 to the fourth times 0.4 to the first. Now we do 5. 5 choose 5 times 0.6 to the fifth times 0.4 to the 0. And you can add those up. We already did one of them, though. We already did 5 choose 3. We already did this one above. So I'm going to leave it to you to fill out the rest. We're going to add those together, and we get about 0.9130. Now, if you were going to use the TI, you could do, since we don't want 0 or 1, we could do a binomial CDF and subtract off those. We subtract off the ones that we don't want, and that leaves us with what we do want. I think it'd be much easier to just use that website, though. Okay, if I use that website, I would say the probability of success was 0.6. And number of trials, there were 5. Number of successes, we're looking at 2 as our number. So if we want at least 2, we're looking at greater than or equal to. So there's my number right there, 0.913, about 0.913. Mean and standard deviation, it's kind of nice they give us these formulas. These formulas are specific for binomial distributions. We had a different way of doing distributions for that's kind of a generalized way of doing it last lesson. We made a table, we found the X numbers, we found the probability numbers, we multiplied them, we subtracted, we did some stuff, okay? But for binomial distributions, we've got these formulas, and that's going to make it nice because it's shortcuts, basically. We've talked about significantly low and high before. Remember, mu is the mean, and sigma is the standard deviation. So it's going to be the mean plus 2 standard deviations or minus 2 standard deviations. Number 5, talking about the NFL games, and it's the same numbers pretty much, 460 overtime, probability was 0.5. It says find the mean and standard deviation. Well, we've got a formula for mean. Mean is n times p. So in this case, n is 460, and the probability was 0.5. So when we multiply, that's 230, or 230 games. That's the mean, the expected value. Standard deviation, that's sigma, and our equation for that, square root of n times p times q. So n was 230, p was 0.5, q was also 0.5. Multiplying there, we're going to get square root of 115, which is about 10.7. There's our standard deviation. Part B says use the range rule of thumb to find the values separating numbers that are significantly low or significantly high. Remember, significantly low was mean minus 2 standard deviations. Significantly high was mean plus 2 standard deviations. So we're looking at 230 minus 2 times 10.7, which is 208.6, and 230 plus 2 times 10.7, which is 251.4. Anything in between here is not significant, but anything out here is significantly high, and anything out here is significantly low. Part C says, is this 252 overtime wins significantly high? Well, yeah, it is. Yes, because it is higher than 251.4. Now, the last things we've got, this is kind of review. I wish this was earlier, but we talk about significantly high again, and we're comparing this to the number 0.05. Probability of X or more is less than or equal 0.05, significantly low. The probability of X or fewer is less than 0.05.